Dear colleagues, we reconvene with the neutrino experiment session, and the first talk today is by D.Moore from Yale University about the search for massive neutrinos with mechanical quantum sensors.
Okay, so hopefully you can see my slides and hear me well. So yeah, thank you for the invitation to give this talk. Of course, I would love to be there in person, but I'm happy to have the chance to participate remotely. So I'm going to be telling you about some experiments that we're proposing to use a new sort of tabletop AMO scale sensor for neutrino physics. And some of these ideas are, old, but maybe the new thing here is that we're trying to use what you see in the picture here, which is a 100 nanometer optically trapped dielectric particle at the focus of a laser in which we can emit radioactive isotopes that can emit neutrinos and then reconstruct the kinematics of decays occurring in those sensors. So because this is maybe a little different technology than many of the traditional detectors we use in neutrino physics, I wanted to start with a kind of quick overview of levitated optomechanics. And in particular, really, there's been a huge amount of progress in recent years to be able to optically control and measure the positions of what I would call macroscopic, but really, femtogram to nanogram masses in optical traps. So taking many of the techniques that for many years we've used for trapping single atoms and ions and extending them to much more massive objects. And this goes back many years to work from Arthur Ashkin, but with relatively modest laser powers, just by focusing a laser, you can trap femtogram objects in a highly focused beam. So this plot on the top is showing one of these 100 nanometer particles trapped. If you want to go to larger objects, it actually is easier to levitate them using the radiation pressure of the laser to hold it up against gravity. But with relatively modest changes, you can trap particles anywhere from a femtogram in mass up to 30 nanograms. So this is a huge range of masses that allows us to explore very weakly interacting forces with different targets in the lab. So SICORSE is a very common tool in biophysics and has allowed us to measure piconewton scale forces and really understand how motor proteins and other things work in biophysics. But if you get rid of the thermal fluid that those optical tweezers worked in and go to ultra high vacuum, then you can essentially eliminate thermal noise while still working at room temperature, and you get to really extreme force sensitivities. So for these femtogram particles, really down at the yoctonewton, or 10 to the minus 24 Newton scale, and for these larger particles at the zeptonewton, or 10 to the minus 21 Newton scale. So this is the last I'll use SI units because it's actually much more natural to switch to fundamental particle physics units when you're talking about these tiny sensitivities. And the key thing here is that in ultra high vacuum, these masses are thermally extremely well isolated. That's why they have extremely good force sensitivity, but they're also electrically isolated, so we can control their charge state and prevent them from coupling to things we don't want them to. And of course, as I mentioned, this is really pioneered based on this levitation trap is exactly the sort of first trap that Arthur Ashkin built and that he shared the Nobel Prize for a few years ago. So the really exciting thing that's happened in the past maybe 5 to 10 years is that we're now able to control these particles so that we're limited really by the measurement process itself rather than any sort of thermal or technical noise sources. And so it's been demonstrated that the dominant noise in these systems when you're watching this 100 nanometer particle in your optical trap is really limited by the photons you're using to look at the particle. Of course, as we know from Heisenberg, if you want to see where that particle is, you have to shine some photons on it. You turn up your laser to get away from shot noise, but then at some point there's back action that pushes the particle and displaces its position and momentum, and that gives us some standard uncertainty relationship for how well we can tell the position of the particle. This plot on the bottom left is showing experimental data. This is the position and momentum quadratures of one of these particles. This is work from Marcus Aspelmeyer's group in Vienna, and they're tracking the trajectory of this quantum particle with a resolution here in the gray dot, which is smaller than the 0-point fluctuations of this trapped particle in the harmonic potential. So This is showing you can cool essentially by looking at the particle and damping its motion. You can cool it to the ground state of that potential. But for sensing applications, it also means that you can resolve momentum kicks to this particle at the so-called standard quantum limit, or limited by your measurement uncertainty. And if we switch from SI to fundamental units, that corresponds to momentum sensitivities for these large spheres, 10 micron diameter spheres of about half an MeV per C, or for these 100 nanometer spheres of keV, tens of keV. And so if you imagine looking then, as I'll talk about, for particles carrying an MEV of momentum, such as a neutrino emitted in a beta decay, you can imagine measuring the momentum of a single neutrino with very high signal to noise. So this is quite exciting. And I should also say, of course, even though this is called the standard quantum limit, it's not a limit. This is only a limit if you're weakly measuring both position and momentum, and it might be possible to go beyond this by squeezing or other techniques in the future. So this is our group at Yale. Again, these are experiments that live on optical tables in our lab. So it's a relatively small group of folks working on this. This is what the setup looks like that we're currently operating. We have several optical traps able to trap a range of particle sizes. But the traps are relatively simple, especially compared to experiments using cold atoms or other kind of traditional AMO systems. There's a relatively limited amount of optics on the table to focus and orient the laser coming through our trap the particles, and then we just use the light scattered by the particle to infer its position. Again, those photons are entangled with the motion of the particle, and we can use that to read out the particle's position at limits of dictated by quantum mechanics. Once we get these things trapped, they're also very stable, and we've trapped single particles for month-long time periods at the base pressures of our chamber. So to give you a little flavor of how this works, again, this is relatively new technology, but the first thing that's different than biological optical tweezers, if you have to get the particles in the trap. Usually they just float by in your fluid in biology, but here we load them on a glass slide. It's actually quite hard to pull them off the slide, but we shake that with a piezoelectric transducer and can pop them up into the laser trap, at least for our larger particles. Here you see us repeatedly trapping the same particle over and over. It comes out of focus when it gets pushed up into the laser trap, and then we can set it back on the glass and actually repeatedly trap the same particle. The next step, as I alluded to, is that we can pump this down to high vacuum, and then we want to be able to make sure there's no stray electric fields or other background forces other than the forces we care about. But we can control the electric charge on these particles with single electron precision. When we pull them off this glass slide, they tend to have excess net charges of maybe 10,000 electrons from triboelectric charging, just frictional charging as you pull them off. But we can shine UV light on the particle, knock electrons off. In this case, if you look over time, we actually knock too many electrons off. So we have more protons than electrons on this nanogram mass. And then we can knock electrons from gold electrodes surrounding the trap back on. And if you zoom in here at the end, you can actually see these discrete steps. This is applying an oscillating voltage to this particle of about 1 volt per millimeter, so a relatively modest electric field that causes a force on these discrete changes in the net electric charge of the particle. So this tiny step here, which we can easily resolve in a 1 second measurement, it's about 200 attonewtons, or less than 10 minus 15 newtons. Once they're trapped and perfectly neutral, so they have exactly the same numbers of electrons and protons, we can optically spin these particles. Even if they have a monopole charge of 0, they'll still have dipole moments in their electric charge distribution. So we actually use circularly polarized light to transfer angular momentum to the spheres and spin them up to megahertz frequencies. Here you can see one of these spheres spinning up over a day-long time period to about 4 megahertz. And actually, if we went any faster, these would explode from centrifugal force. So this is about as fast as we can spin solid objects of these sizes. And that's good because it gyroscopically stabilizes the orientation of the particle. So if there's any non-sphericity in the particle, we can keep that stable. And it also averages away any permanent electric dipole moments that aren't along that axis of spin direction. Okay, I know this is quite a bit, but all these technologies are important for making these experiments work. The next step is, if we want to, we can actually cool the motion of the particle. Again, by measuring its position, measuring the photons scattered by the particle, we can infer its velocity and apply a cold damping or a negative force to damp that velocity, as though we were damping its motion, but in a cold way that doesn't add noise. And we can, in our current system for large particles, cool to effective temperatures of order 50 microkelvin. So this is only the center of mass degree of freedom that is cooled, but it's still as though the particle were in thermal equilibrium with a 50 microkelvin gas. And that's also can translate to our force sensitivity that I talked about earlier. And then last, if we want to, we can further average over this electric dipole moment that we've already stabilized by spinning this thing at megahertz frequencies. by essentially doing the classical analog of pi pulses in NMR, where it can apply a perpendicular electric field, and we've shown we can rotate this orientation of this gyroscope and average over its dipole or higher order multiple moments. So putting all this technology together, then of course what we're interested in our group is what we can do for fundamental physics measurements, and in particular here, neutrino physics measurements. So the classical thing with these systems is to search for fifth forces, test Newton and Coulomb's law, and this work is underway in our group as well as Giorgio Grada's group at Stanford. It's also done the world's best search for millicharged or fractionally charged dark matter particles bound to positive nuclei in terrestrial matter. We haven't seen those, but I'll advertise the paper. You can also set limits on the sum of the proton, neutron, and electron charge and check charge quantization. But what I'll talk about in this talk is trying to see tiny kicks to these spheres, and in particular, if we implant radioactive nuclei, can we see fully reconstruct the kinematics of any invisible or non-detected particles leaving these spheres by measuring the recoil of the entire object after that nuclear decay. And this is based on this recent paper that showed up earlier this year. So the idea here is to take these same optomechanical systems that are now reaching these quantum measurement regimes, dope them with isotopes of interest. And this is maybe not a completely new idea to kinematically reconstruct optically trapped particles, especially for single atoms or ions. But the nice feature of using these glass particles is that it gives us a way to hold on to the species of interest, that we don't have to, tune our lasers to pull some specific atomic transition coupled to the nucleus of interest. We can just shove whatever we want into this glass matrix. And we found that we can get the sensitivities, even with these much larger particles, to be able to reconstruct, as I said, with high signal to noise, the momentum of maybe a single neutrino emitted in a beta decay, or even better in an electron capture decay. If we have a captured electron, then a neutrino will leave this particle, and essentially this nucleus will stop, the nuclear recoil will stop fully, even in these 100 nanometer particles, and by momentum conservation, the entire particle will recoil with momentum nearly equal and opposite to the emitted neutrino. So of course, I'll focus here on sterile neutrinos, which are our favorite, maybe invisible particle to go look for in these sorts of searches, but I should say that this is, a generic principle, and any other quote unquote invisible particles that might be emitted in these nuclear decays should also be in principle searchable with these methods. And so the concept is to take one of these optically trapped particles, and in fact, in the future, we want to scale this and are already scaling these to large arrays of particles instead of just single particles, surround them with traditional charged particle detectors to detect either the emitted beta, reconstruct the three momentum of this emitted beta, or tag as a trigger the Auger or X-rays coming out in these electron capture decays, and then correlate that with the recoil of the sphere itself to reconstruct the kinematics of the full decay. And I should say this is also being done by the Beast collaboration in superconducting sensors, but this would be the maybe first proposal to do it with these levitated optomechanical systems, which builds on previous ideas to do this with trapped neutral atoms and ions. So what do we know about sterile neutrinos? In the laboratory especially. So this is a nice summary plot from a few years ago showing essentially the mixing of the sterile neutrino with the electron type flavor. This would be, in these case of these weak nuclear decays, the branching ratio to a decay where a heavy sterile is emitted versus the mass of that heavy sterile. There's some cosmological limits here, but if you look at the laboratory limits, which are the colored lines, in this range that we're most interested in from kind of keV to MEV masses with these experiments with nuclear decays from beta decays or electron capture decays, the best existing limits primarily come from looking for kinks in the beta spectrum. So this is a statistical measurement where you reconstruct the entire beta spectrum, look for small breaks in the spectral shape that could be evidence of an additional contribution from a decay to a sterile. There you have to gather many statistics to be able to see these kinds of statistical changes in the shape of the spectrum. And as I'll say, the nice thing about reconstructing the kinematics of individual decays is that in principle, a single or a handful of decays would allow you to be able to identify these decays to heavy states. And as I'll show, we can project that we may be able to go substantially beyond the statistical measurements with the beta decay spectra. And I should say that it's maybe for this audience, it's well known, but keV sterile neutrinos with a small mixing here below the astrophysical limits are a viable dark matter candidate that are hard to probe with known experimental techniques. So what would the signature of this look like if it does occur? So if a KV to MEV mass sterile did mix with the light neutrinos, then we'd expect a small amount of these decays, again, given by the branching ratio on that previous plot, to emit a heavy nu. And so if we were to reconstruct here for an electron capture decay on the left, which is maybe the simplest case, I'll just show this in the interest of time. The expected spectrum versus the reconstructed neutrino momentum that we get by measuring the recoil of the trapped particle. Most of the decays here for argon-37 would produce a momentum consistent with the essentially massless light neutrinos leaving the particle. But if we were to zoom here on the x-axis for a sterile neutrino with a mass of 750 keV, actually at the current best experimental limit from the previous plot, then in just a month of data with a single sphere, we'd expect to see a highly significant signal. And I'll talk about backgrounds very briefly, but we think the backgrounds may be essentially zero with this technique, so they could be very, very low. So we can use that kind of simulation to project our sensitivity to heavy sterile neutrinos emitted in these nuclear decays. Again, this is a plot showing that mixing or essentially branching ratio to the sterile state versus its mass. For a few different beta decay isotopes that we could implant on our spheres, these are common isotopes found in many, let's say, biology labs. And the exciting thing is that if you compare it to the gray lines here, which are existing spectral distortion searches in the laboratory, with just one sphere in a month, we could already maybe probe 1 or 2 orders of magnitude beyond the best existing searches. Of course, this is not yet demonstrated. This is just a projection. But if you really then think about where this technique could be scaled and what the backgrounds might be, you can imagine taking these same curves now on a log horizontal scale here. This red curve here is the same as the left. Scaling this to maybe 1,000 nanoparticles read out for a year, we could get down to many, many orders of magnitude below existing sensitivities. And we think that, we'll have to see what the backgrounds are for these experiments, which could ultimately limit the sensitivity. But in principle, there's a triple coincidence between the sphere recoiling, detection of the secondary particle on our particle array, as well as seeing a change of in the electric charge by 1 or more units of the particle that could allow us, we think, to reach background levels even below what we're projecting here. So we still have to demonstrate that, but it's relatively promising. So I'll just very briefly say, the dream here would be to actually be able to reconstruct the mass of the light neutrinos, the standard model neutrinos with these same sort of techniques. However, there's real constraints from quantum mechanics if you want to do that. Again, this, just related to this Heisenberg uncertainty that I talked about at the beginning, if you wanted to measure differences in momenta at the millieV or 100 millieV level, you need to delocalize your particle, or you need a particle that has a state that's delocalized by at least 2 microns. So a solid 100 nanometer object can't do that. No solid source could do that. This has been pointed out for relevance to C nu B detection recently in the Ptolemy experiment by several authors. But these optomechanical systems might present a path around that, although it's very ambitious and far beyond the state of the art, is that you could take the center of mass of this entire solid particle, squeeze its motion maybe by 20 dB. Again, this is large levels of squeezing, but not beyond what you might dream for in this field. And you might then be able to measure momentum differences as small as you would need to resolve the different momentas of the light neutrinos. That said, though, you still need to find a source of low energy neutrinos that come out of these nuclear decays. And so we'd also have to find presumably better isotopes than tritium for doing this. So it's not clear yet if this is viable, but it's at least fun to think about. Okay, so let me stop there. I think these new optomechanical systems that are reaching quantum measurement regimes are really interesting for a variety of fundamental physics applications. And one of them that's relatively generic is to reconstruct the kinematics of nuclear decays. This gives us a nice way to hold on to a lot of nuclei, which could decay by emitting sterile neutrinos or other invisible particles that we might be interested in. And I think we're really at the early stages of this. We can imagine scaling these to really large arrays of particles, and future sensitivities are very promising. So thank you very much.
All right, let's thank the speaker. Does anybody have any questions? Are there any questions online? All right, let's thank the speaker again.
Thank you.
And the next speaker is Dr. Samoilov from PNPI about the preparation of the neutrino 4 experiment at the SM3 reactor.
Thanks, organizers, for opportunity to make this talk about preparation of the neutrino 4 plus experiment. So the goal is to search, goal is the same, search for stereo neutrino. And a neutrino 4 experiment has had some positive result in these searches, but confidence level is not enough. So this result has a good agreement with gallium anomaly and the result of the Beth experiment, but with other experiment, some other experiment agreement is not so good. Anatoly Pavlovich Serebrov in his report told about some reasons of that, but in any case, we need to clarify the situation around this, and we hope we confirm our results with confidence level up to 5 sigma. So for that purpose, we built a second laboratory at the SM3 reactor. SM3 reactor is a great place to search for EV scale stereo neutrino. We already have laboratory there. First laboratory is here, and beside the building of the new one laboratory, we will improve our experimental setup at the first laboratory also. Both laboratories are organized in a similar way. A sectional detector with PMTs filled with liquid scintillator inside the passive shielding and covered by active shielding move on the platform back and forward to the SM3 reactor, so we can detect reactor antineutrinos and measure its flux and spectrum at different distance. The both laboratories organized similar, but there are some difference in detector scheme and passive shielding and transport system, but new version of active shielding, data acquisition system, and the high voltage distribution system are the same for both laboratory, and we use the same equipment to build new one and the upgrade the first one. To upgrade the first one. So high voltage distribution is system for tune of each PMT by regulation of high voltage, and this system allows us to control and keep it stable, tuned gain of the each PMT, keep stable up to 0.5% accuracy. So the modernization of this system is practically technical, only a form factor and some interface are changed. But we built a 50-channel prototype for testing new equipment like active shielding, data acquisition system, and high voltage distribution system, and master interface model and distributor model are installed on this prototype. For the upgrade of the new of the first laboratory, modules are ready, and for the new laboratory, modules are being manufactured at the moment. The more interesting changes in data acquisition system. These all electronic systems are developed in our institute in electronic departments. So they renew data acquisition system cross 3, new digitizers with new flash ADCs allow to get 3 times faster sampling rate, up to 12 megasamples per second, and the new interface board on the concentrator board allows to transfer rate increasing by up to 10 times. Also, we had some problems with the purchasing of some electronic equipment, and then therefore we need to change the scheme of the amplifying also, and adapter boards. The problem was solved. The new boards, new scheme was developed, manufactured, and it's ready to install. So here's full-scale installation on the our 50-channel prototype. Active shielding is consists of plates of plastics insulator with optic fiber in it, and CPM and necessary electronics are installed on each plate. Plates cover detector and both new laboratory and the first one covered all, but beside the bottom side. So to introduce the signals, the data from active shielding, avoiding significantly increasing of the amount of data, this electronics was developed, the code for the data from active shielding, and introduce it in minimal way to data acquisition system. All active shielding was manufactured in IHEP institution in Protvino, and received with great help from Laboratory of Nuclear Problems of JNR. So the active shielding all plates already in Dimitrovgrad at SM3 reactor. Passive shielding of the first laboratory will be the same. Here's some difference. That passive shielding is stationary. It consists of lead borated polyethylene and iron, and the detector move inside this passive shielding. And in new laboratory, passive shielding will be installed on the platform and move with detector. And our some Monte Carlo calculation shown here show us to that copper instead of lead could be a good solution for decreasing of fast neutron background. So we replace a new passive shielding for the new laboratory, led by copper. So this passive shielding also manufactured and moved to Dimitrovgrad, and already part of it already installed in a new laboratory. The detector for new laboratory also sectional, like the previous one. It consists of assembled light guides installed in transparent vessel and installed in case. PMTs in magnetic shield attached to the case this way, both sides of the each light guide. More detailed of the preparation of the new laboratory in this publication you can find. So and the detector of the first laboratory, scheme of it remained the same. It also sectional, but PMT only from above. But in both detector, we will be use a new scintillator, which was developed in collaboration with Institute of Reactive in Moscow. It is lab-based scintillator doped with gadolinium, concentration of gadolinium 2 grams per liter instead of 1 gram per liter, which was in the neutrino flow experiment. And also disopropyl naphthalene was added to get some pulse shape discrimination capabilities. We had some Niels we had some scintillator from Niels collaboration. They kindly gave us 400 liters, so we can compare it. So area scintillator from area has the same qualities, has the same pulse shape discrimination capabilities, and this this level of pulse shape discrimination resolution of the EAT parameter allows to reduce correlated background up to 4 times, and the signal to background ratio will be 1 to 2, depend on the position of the detector. And increasing gadolinium concentration allows to reduce accidental background almost 2 times. We had some problems with purchasing PMTs, which we plan to use from Hamamatsu's their sad story, but with the assistance of Professor Jun Chao, which helped us to contact with North Night Vision technology company, which sell us right amount of PMTs with the same similar characteristics, PMTs on MCP based, and we already get them, and measurements shows that it's a very good replacement of the Hamamatsu's PMTs. And the last improvements is a system of optical calibration and monitoring based on these crystals. It's gadolinium, aluminum, gallium, garnet crystal with a small amount of americium 241 isotope. So this is calibrated source of light, which will be installed on around each PMT. So it these crystals allow us to control the stability of each channel, measurement channel, non-stop online, because of signals from this crystal is easily distinguished by the pulse shape discrimination technique because of light production features of the gadolinium of the GAC crystal. So, conclusion, we get news insulator in amount of 10 cubic meters. It already delivered to Dimitrov. We have all equipment for the modernization of the first laboratory, and this process will start in September after this conference. Transport system and part of passive shielding are already installed in new laboratory, and electronic system of high voltage distribution and data acquisition are being manufactured, and by the end of the year we expect we build new laboratory, and all improvements totally allow us in new laboratory to achieve accuracy almost 3 times higher than in neutrino 4 experiment. Thanks. That's all.
Right. Does anybody have any questions?
Thank you for your talk. What energy resolution do you expect to have after all the improvements?
Resolution will be mostly will be the same as in previous, because we do not change this scheme with optical contact, so we cannot establish some improvements in resolution.
As far as I understand, you will have 2 PMTs now, and in the future. And now there's just 1 PMT per section. Will this help, or?
It helps. It helps with pulse shape discrimination. It helps with reducing accidental background by better position reconstruction, and it helps.
All right.
Thank you. In your last slide, you showed some improvement just before. Yeah, here. So could you tell what was the level of systematic uncertainties in present situation, present data taken, and what level of systematics you expect after this improvement?
Now it's hard to tell. At least we hope it not be the worse systematics. Remain the same, maybe, I suppose. It's only this improvements, this accuracy is about statistical mostly. Our problems is mostly low signal background ratio. It's less than 1 in neutrino 4 experiment, and without any improvements of statistical accuracy, there is no point to find the.
This low ratio exactly goes to systematics.
Once again, I suppose if we had very bad statistics, systematics is this at least the second, maybe lower problem.
Still, my question, what is the level of systematics now? Just number, if you remember.
In percent?
Yeah, now in neutrino form.
We don't estimate this systematic like this like in I can tell you the one number.
Okay, thank you.
Any more questions? All right, let's thank the speaker. And we continue with a talk by Dr. Skrobova, Lebedev Physics Institution, about the measurements of the reactor antineutrino energy spectrum dependence on fuel composition and absolute antineutrino counting rates.
Thank you. So first of all, I would like to thank the organizing committee for the opportunity to present these results. And I'm going to tell you about fuel evolution and absolute counting rate studies with the dance detector. So the motivation is the following. Several speakers already mentioned the reactor antineutrino anomaly. There are measurements of uranium-235 to plutonium-239 cross-section ratio by the Diabay collaboration. And this cross-section ratio is smaller than in Huber and Müller model. Recent measurements from Kurchatov Institute support Diabay results. And the next point, using absolute counting rates, we can search for sterile neutrinos and large delta M square values. So this picture shows the correlation between the reactor thermal power and IBD counting rates measured by the dance detector. And stable performance of the dance detector allows us to perform such analysis. So first of all, I would like to remind you that dance detector is located under the reactor core on the moving platform, and inverse beta decay reaction is used to detect antineutrinos. In case of commercial reactor, we have very high antineutrino flux, a large core, and typical fuel components are the following. This picture shows the typical fuel evolution during the campaign. And on the right, this is the antineutrino energy spectrum for different fission isotopes. So you see that this spectra a little bit different, and since the fission fractions change during the campaign, we can observe fuel evolution. So I will start with relative measurements, and the first thing I want to discuss is the derivative of the IBD counting rate with respect to plutonium-239 fission fraction, and I call it relative slope. So how we get it? We have a positron spectrum, observed positron spectrum. This positron spectrum is split into several energy intervals, for example, 1, 2 MeV, 2, 3 MeV, and so on. The whole data set is split into several intervals depending on the plutonium-239 fission fraction. This is the horizontal axis. And finally, this relative slope is calculated. This is normalized using the 0.3 plutonium-39 fission fractions. And we can compare these results with the diabase. So this is the dependence of the relative slope on the energy interval. Magenta points are the results from the dance experiment. The violet line shows our Monte Carlo based on Huber and Müller model, and blue points are Diabase experiment and Diabase Monte Carlo. So this is there is and another way to look at the same data. We can look at the IBD counting rate normalized at using the 0.3 plutonium-39 fission fraction, depending on this fraction for the whole energy interval. And here we see that IBD counting rate dependence on the plutonium-239 fission fractions for various energies agrees well with Huber and Müller model. And it's a little bit steeper than the Diabase results. So this calculated slope will be used in further measurements. Now I'm coming to the measurements of the uranium-235 to plutonium-239 cross-section ratio. So first of all, the IBD counting rates are proportional to the total to the product of the total cross-section and the fission fraction. This is uranium-238, plutonium-241, uranium-235, and plutonium-239. So after several calculations, we can express the uranium-235 to plutonium-239 cross-section ratio using the slope measured in the previous slide, and the fission fractions from our reactor, and the unknown and other cross-section ratios, which are taken from Huber and Müller model. As a result, we obtain the following value. This value obtained by the dance experiment is somewhat larger than the results from the Diabase collaboration, but our result is in perfect agreement with Huber and Müller model. So maybe it's too premature to say that reactor antineutrino anomalies solved by the wrong uranium-235 to plutonium-239 cross-section ratio. Now I'm coming to the absolute results, and absolute counting rates can be expressed with the following formulas. So here we have the number of protons, the efficiency, the solid angle, which includes the integration over the detector and reactor. We have the IBD cross-section dependence on energy, and the antineutrino flux, which could be expressed using the reactor thermal power and mean energy per fission. And here we have the fission fraction and the energy spectrum per fission for different isotopes. And here is also the term for neutrino oscillations. So the main question here is systematic uncertainties. So this table shows the systematic uncertainties which play the role in analysis with absolute counting rates. So the main uncertainties come from the number of protons and the selection criteria, and of course from the fission fractions. I want to draw your attention to the fact that all these uncertainties are given in percent according to the contribution to the absolute counting rate. And of course, another one important uncertainty comes from the antineutrino flux prediction. This could be estimated conservatively as 5%. So the total uncertainty, including flux prediction, is about 7%, and total uncertainty, including without flux prediction and just for using detector features, is 4%. So now I'm moving to the results. This is the comparison of the predicted and observed dance IBD rates for up, down, and middle positions. The magenta points are dance results. The sign line is the prediction based on Huber and Miller model. And the band shows the systematic uncertainty of 4%, excluding the flux uncertainty. So the dance results are below the Huber-Miller prediction, but within the expectation. So let's zoom in, and here is comparison of the IBD counting rates, these magenta points, with Huber and Miller model, and with the model using the Kurchatov Institute data. So once again, model uncertainties are not included here. It's just our experimental uncertainties, uncertainty of 4%. And in case of Huber-Miller model, as I already said, our data is lower than predictions, but within the uncertainties. And in case of Kurchatov Institute model, our data is larger than predictions, but also within the uncertainties. Okay, now I'm moving to the sterile neutrino oscillation analysis. As it was already shown today, our test statistics is defined in the following way. These terms are responsible for analysis without absolute counting rates. And in case of analysis with absolute counting rates, we add the following term to the chi-square. This depends on the absolute counting rates. And in this kind of analysis, we use a very conservative estimate, including the flux uncertainty. So the overall total systematic uncertainty is 7%. Here are the results. These are the exclusion limits obtained with a Gaussian CLS method. Large and interesting fraction of parameter space is excluding using just model independent analysis. This is exactly the same results that were already shown by Igor today. And with absolute counting rates, the exclusion area expands to the large delta M square values. And the exclusions with large delta M square values are consistent with previous results with such types of analysis. So here we can conclude that our the dance preliminary result excludes the dominant fraction of the expectations from the best experiment, these gray areas, and the best fit point from the neutrino 4 experiment. These results depend on the neutrino flux models. However, we estimate a relatively large systematic uncertainty of 5%. So I'm moving to the conclusions. So the absolute antineutrino counting rates smaller than predictions with Huber and Müller model, and but consistent within errors. Here is the ratio. They observed absolute counting rates are larger than predictions we were using the Kurchatov Institute model. Here is this is the ratio. The relative IBD counting rate dependence on the plutonium-239 fission fraction is consistent with the Huber and Müller model and slightly steeper than the Diabay results. And the calculated ratio of the uranium-235 to plutonium-239 cross-section ratio is consistent with the Huber and Müller model and slightly larger than Kurchatov Institute results and Diabay results. Our oscillation analysis with absolute counting rates based on the Huber and Müller model excludes practically all parameter space preferred by the best experiment and the best fit point of the neutrino 4 experiment. However, these results depend on the predicted antineutrino flux, but here we use a very conservative uncertainty in the flux of 5%. So that's all. Thank you very much for attention.
Right. Does anybody have any questions? And online? All right, let's thank the speaker again. And the next talk is by Dr. O.Razuvaeva about the Red 100 results and prospects.
Okay, hello, I'm O.Razuvaeva and I'll tell you about Red 100 experiment. So first of all, I want to speak about coherent elastic neutrino nucleus scattering at CERNs. It is a process which was predicted by a standard model about 50 years ago, but because of extremely low energy of the recoil nucleus, it was observed experimentally only 5 years ago. There are a lot of motivations of experiments, such as fundamental physics, standard model verification, and there are practical goals of CERN studies, like monitoring of nuclear reactors. On this slide, you can see a spectrum of neutrino energy from nuclear reactor and recoil nuclear spectrum. And then I want to tell about Red 100 experiment. It is a two-phase emission liquid xenon detector, which is sensitive to a single ionization electron, single electron signal, and a coherent elastic neutrino nucleus scattering signal is expected to be of several electrons. There are two arrays of photomultipliers and 19 photomultipliers in each array on the top and on the bottom of the target volume. So Red 100 was deployed on Kalinin nuclear power plant. It was placed 19 meters from the reactor core and surrounded by a passive shielding. The physical run of this detector is 2022. So there are a lot of another neutrino experiments on Kalinin nuclear power plant, like NuGen, iDream, and DANCE. First of all, I want to tell you about external background, which we have measured using different additional detectors, and so using RED 100 also to there's no significant correlation in external background count rate with the reactor operation. You can see plots of external background here, gamma background, neutron background, and muon background, which was measured by RED 100. So on the right, you can see pulse shape discrimination plot, which helps us to discriminate neutrons from gammas when we measure neutron background. But the main background in our region of interest, and I will repeat that our region of interest is several ionization electrons, is spontaneous emission of single electrons after large signals in our detector. In order to block large signals from cosmic muons and to minimize short component of single electron emission, we used a custom technique named electron shatter, which block signal from after muon ionization signal after large scintillation. But we still have significant background part, which consists of random coincidences of several spontaneous single electrons. So in this case, signals from neutrinos are most point-like events. So you can see on this illustration, and background events are mostly not point-likes, like these two electrons, which come to electroluminescence gap simultaneously. So we performed two deep learning models to mitigate this kind of the background. So for simulated test data set, we have these results about 90% of background suppression and 10% of sound suppression. But in real life, things are a little bit more complicated. So let me tell you some words about real data. We have both reactor on and reactor off data. So, and we are doing blind analysis. It means that reactor on data is closed until all the data analysis methods are ready. We use reactor off data to check stability of our detector. So on the right, you can see stability of single electron signals, duration, light yield. So also we check other parameters. Then we apply optimize cuts on our reactor of data and apply our neural networks in order to suppress background. So we optimize a radius cut, we optimize duration cut. And also we use a three-dimensional likelihood fit in order to calculate sensitivity. On these pictures, you can see the dimensional distribution between two predictions of our networks. A prediction of networks means probability to be point-like for each event. And you can see that there is a highly correlated background events, which means that there are a lot of point-like events in our background. I can say that this is not only thing which have influence to our result. Also, we also measured electron extraction efficiency, and it it have great influence on our result. On the right, you can see plot with comparison with results of other collaborations. Also, we have measured electrons lifetime using muon data. So then after optimizing all cuts and neural networks, we expect sensitivity, like we can register sound signal if it will be a few times greater than the standard model predictions. And here you can see table with background and sounds rate in using optimized cuts. So and now Red 100 is in the MEPhI, and we are going to change our target material to liquid argon. So we will use TBB as a wavelength shifter, and then we will try to make new experiment in order to study its elements. So then short conclusion that Red 100 was successfully deployed and run and at Kalinin NPP. Now data analysis is ongoing, and we hope that we will present our results as limit for the seventh cross section soon. Now detector was shipped back, and we were doing the upgrade of the detector, and we are planning to make Red 100 with liquid argon first tests this year. Thank you very much for your attention. Your question?
Does anybody has questions? All right. I have a question. I have a question actually. So you are using a cut on some variable that is trained on the data set, right? On some training data set.
Sorry? Yes, we use training data set in order to train our neural networks. Yeah, it was simulate using it's a rather complicated process which of simulation our data to train. So we use light response functions which we measure experimentally. Then we simulate single electron events using these light response functions. Then we construct events from simulated single electron events, and then we train our networks on these data set.
So actually the question was whether do you consider any dependent, so any distortion on the spectrum that is done by cuts with usage of such a variable. So this is like energy dependence or whatever.
Distortions in real data. So in science data, you mean? We have simulated science data set, and so we applied all cuts to simulated science data set, and so calculate influence of cuts to science data.
Thank you. So if there are no more questions, let's thank the speaker again. And the next talk is by Dr. E.Khalikov from the Moscow State University about the recent results from SND at LHC.
Thanks. All right. So I'm going to talk about the recent results from the SND detector that's located at CERN. May I? How do I change the slides? Oh, right. So sorry. Okay. So yeah. Basically, SND is an experiment that's based on LHC, and in LHC there have been a neutrino physics program dating back to 1980s, and you have there are some references that are on the slide. Well, mainly this interest in neutrinos was driven by the goal to register the tau neutrino, which was later achieved, but not but elsewhere. But still, the program. The neutrino program was there. Basically, why detect neutrinos at LHC? Because proton-proton collisions can produce large neutrino fluxes in the forward direction, and the neutrinos could be of very high energy. So as you can see, 10 to the power of 2, 10 to the power of 3 GeV. And basically, this some kind of small-scale LHC experiment can observe neutrinos of all 3 types. So now, currently, the 2 neutrino experiments that are operating at CERN at LHC are SND at LHC and Phaser new. And I'm going to talk about the first one. So the SND at LHC experiments, that's basically scattering and neutrino detector at the LHC. It's a detector that was constructed to measure the high energy neutrino interactions of all 3 neutrino flavors from the LHC in the TeV scale. So it's located in a former transfer line in a tunnel called TI-18. That's a former transfer line from SPS to LEP, and basically it's 480 meters away from the Atlas interaction point. It's so the flux itself is it? No, wait. How do I point? Sorry. This one. Nope, wait. Oh, okay. Sorry. I thought. All right. So as you can see, it's basically the detector is located slightly off axis. So the neutrinos that propagate and enter the detector go through these LHC magnets as well as 100 meters of rock. And they reach the neutrino detector. The angular acceptance of this detector is in the pseudo rapidity range of 7.2, between 7.2 and 8.4. Okay, so the detector is structured like this. It's a hybrid detector, and it has 2 parts. It has the emulsion the part and the electronic part. Well, I mean, and also a veto system. So basically, the veto systems are 2 planes of scintillating bars, and then comes the vertex detector plus target plus electronic colorimeter, which is presented by the target is presented by 830 kilograms of tungsten, arranged in plates that are interleaved with emulsion material. So emulsion cloud chambers, yes, they are interleaved with tungsten and they are used in order to reconstruct the neutrino vertices. And then there are also 5 sci-fi planes that are sliced in between the emulsion detectors in order to account for the calorimetry and the timing. And then there's also the muon system and the hadronic colorimeter, which consists of 2 parts, 8 in total plastic scintillator planes that are divided into 2 parts, upstream and downstream, and they are interleaved with iron walls. So here the main hadronic colorimetry takes place, and the hadronic showers are registered and analyzed. So basically, the physics program of the experiment, it's it's neutrino interactions. It's registering neutrino interactions in the TeV range. So as I said, this detector is able to register all three flavors of neutrinos. And then there's also measuring the neutral current to charge current ratio. Then there's also heavy flavor physics and some dark matter objectives as well. So with heavy flavor, it's the goals are to study the neutrinos that come from charmed hadron interactions, charmed hadron decays. Sorry. So because that's 90% of the electronic neutrinos and anti-neutrinos that reach the detector, and basically the goals are to measure proton-proton to electronic neutrino cross section, and then measure forward charm production, and then to constrain the gluon distribution function at very small x. Then there's the test of flavor universality with using the ratio of different flavors of neutrinos. And then there's also the beyond the standard model goals, which are mainly centered around finding FIPs or feebly interacting particles, registering them and their decay in the detector. So now the timeline. The letter of intent was first published in August 2020, and in a very swift timescale. The experiment was approved by CERN in March 2021. Then the detector was installed in December, and in April 2022, it has successfully started taking data. So the data that was taken in 2022 is as follows. It's the total recorded luminosity is 36.8 inverse femtobarns, and there were also additional data collected in 2023, but right now it's not being collected due to some I think due to the fact that Atlas has stopped collecting data for a while. So then there were 3 emulsion detector replacements, and the detector operation uptime was about 95%. So this is the data that was measured. Now the analysis strategy, and now we will come to the first results. Basically, but in order to arrive at them, we first need to talk about the event selection criteria and the analysis strategy for these results. Basically, the goal was to get a high purity sample of muon neutrinos, charged current events. Okay. So the strategy for this was counting method and to use the electronic detectors and reject high level background. Of course, the emulsions can also give us the information, and right now they are being analyzed. So the results that I'm going to present today only come from the electronic detectors. So the data set was the full 2022 run, like I said, 36.8 inverse femtobarns, and the cuts that were applied to select the possible event candidates were the first one was the sci-fi. In the sci-fi, we only consider the events that have a neutral vertex in the 3rd or 4th target walls. The first and second are excluded because these could be they could give more muon background, and the fifth one was excluded so that the hadronic shower would have been registered in at least 2 planes of sci-fi. So then there were the side entering backgrounds were rejected, and this gave us the signal acceptance of 7.5%. And then there was a muon neutrino identification, which included large hadronic activity in sci-fi and HCal, basically a hadronic shower, and reconstructed and isolated muon track. As you can see in the picture here, there are some events in the 2 planes of in the at least 2 planes of sci-fi, which represent the hadronic shower, and then a clear-cut muon track in the following muon detection system. So this, yes, a reconstructed and isolated muon track. So the total number of charge current events expected in this data set after the cuts was 4.2, and the background estimation was as follows. Basically, there are two main sources of background. There are 2 main sources of background. It's entering muons. And the background from the neutral hadrons, which were produced by these entering muons. So an entering muon track may not be registered by the detector due to the detector inefficiency, and so we need to take that into account when counting or measuring estimating the background for muons. So the shower that was induced in muon deep inelastic scattering interaction or in electromagnetic activity. So the muons in acceptance is this number, 10 to the power of 8, and the detector inefficiency is this. So that gives us a very negligible background for this current selection. More background is expected from neutral hadrons and from muon deep inelastic scatterings. So their interactions will give us the total background, the total number of background events of the order of 10 to the power of -2, 8.6. 10 to the power of -2, so it's about 10, like 0.1. So yes, so this was the estimated background, and so with this estimated background and with this number of predicted events, expected events from this data set, 8 muon neutrinos have been registered. Muon neutrino charged current candidates were registered with a statistical significance of 6.8 sigma. You can see one of these events here in the right plot, and here you can see the well, this is the comparison of expected hits in the sci-fi plane and the registered hits in the sci-fi plane. As you can see, they're quite in accordance with each other. And yes, so with 4.2 estimated expected events, there were 8 registered. So this only leaves me with the summary and the conclusion for this talk. So like I said, SND at LHC experiment is already measuring neutrinos produced in the LHC in an unprecedented energy range. 100 to 1000 GeV, and so there were successful detector operations in 2022. Some more data taken in 2023, and 36.8 inverse femtobarms of recorded luminosity. And the first results that were yielded from this experiment were 8 muon neutrino candidates from charged current with an expected background with this expected background and high statistical significance. And like I said, there are many interesting studies ahead of the experiment, including of course the neutrino the neutrino measurement and analysis, and even FIP searches. So I guess that's it for my talk, and I would like to thank you for your attention.
Yeah, colleagues, does anybody have any questions?
Uh, 10 to the power 10 to the power of almost 10 to the power of -1. Yeah, yes. Well, these selection criteria and these cuts have been discussed many times during the weekly run meetings, and basically these make sense because if you exclude some of them, then you wouldn't have such clear such a clear, for example, muon track if you don't deselect the events that have cluttered hits in the muon system, or if you don't like if you select if you also select the fifth bar, no, I mean the fifth plane in the sci-fi, you will have, for example, only one play that indicates a hadronic shower. So basically, these were optimized after like a run of meetings. So that's why there are 8 muon neutrinos, but everything is of course is debatable, and as we go on, we also discuss the possible possible other selection criteria and so on. It's a process. There's one more.
Thank you, and congrats on best results. So comparing to Pfizer, what is the difference between your detectors?
Yes, so the phaser has, well, the main difference, I guess, is the difference in the pseudo rapidity range, and then there's also a difference in the layout of the detector. Of course, phaser also uses emulsion, but I don't think I have a slide prepared. So basically, it's detector structure and the pseudo rapidity range that's different.
So I think they also presented this year first results, right?
Yes, they have.
Looks like they have more events. Is it due to the mass difference of the detectors, or what's the reason?
Unfortunately, I don't know much about phaser. I haven't studied it that closely. I can only tell for our events, but yeah, they I know that they have also presented some data that was collected during last year. But unfortunately, I don't have any more information on phaser.
All right, let's thank the speaker again. All right, let's thank all the speakers for their talks.